Merhabalar. Öncelikle hoş geldiniz. Ben bu arada kısaca kendimi tanıtayım ve bugün hakkında birazcık bilgi vereyim isterseniz. Benim adım Elif Zeynep Emir. digiMODE'da satış direktörü olarak çalışıyorum. Bugün sizlere Türkiye partneri olduğumuz SLM Solutions firmasıyla birlikte bir webinar düzenledik. Ve FreeFloat özelliği ile ilgili birazcık bilgi paylaşacağız. Burada ürün yöneticisi Benjamin bize destek olacak. Ben biraz aslında şeyden de bahsedeyim. Sunum esnasında sorularınız olursa lütfen aşağıdaki Question and Answers bölümünden bize yazın. Sunum sonunda hepsini birlikte teker teker okuyup teker teker cevaplandıracağız. Şey esnasında yani webinar esnasında siz oraya istediğiniz zaman yazabilirsiniz. Sunum sonunda toplu olarak cevaplandıracağız. Sanıyorum 5 geçiyor. Artık yavaştan başlayabiliriz dilerseniz. Benjamin, hi.
Hi.
Okay, actually we can start. Would you like to share your screen?
Yes, of course. Let me know when you can see it.
Okay, we can see it.
All right.
Your turn.
All right. Yeah, thank you very much for having me today. I'd like to briefly introduce myself. So my name is Benjamin. I work as a product manager at SLM Solutions in Lübeck in northern Germany. And it's my pleasure today to bring FreeFloat a bit closer to you. I'm quite sure that you've heard a little bit about FreeFloat on LinkedIn or social media or YouTube. But today I would like to give you a closer tour on what FreeFloat is actually about, tell you a little bit about the workflow. But before we dive into that, I just want to briefly take the opportunity and present SLM Solutions to you just once more again, just bringing us a bit closer to you. So who we are, we see ourselves as technology pioneers in the field of laser powder bed fusion, specifically in metal powder bed fusion. So we only focus on metal SLM systems. Dieter Schwarze is basically the co-inventor of the whole SLM process back in 1996. He's still with us. He's still working with us in the company. We're very glad to still have him on board. Speaking of technology pioneers, I think what makes a technology pioneer are, of course, very innovative products, such as we've been the one that we've invented multi-laser SLM systems by bringing the dual laser SLM 280 in 2011 to the market, and the first quad laser SLM 500 in 2013. And just last year, about a year ago, we presented NXG 12600, also the one that you can see in the background, with an unprecedented 12 lasers in a single machine. Furthermore, we do have tons and tons of patents that we're quite proud to have, and we are very much defending those patents. Might be minimal, might be really maximum impact patents, such as the bidirectional recoating process that minimizes laser off time. Of course, when we speak about multi-laser machines, we also have to talk about overlap, and we have a patent on a overlap stitching technology, which guarantees seamless builds with multiple layers throughout the entire build height. And last but not least, when you want to work in a serial production environment, it's very important to have homogeneous part properties throughout the entire build plate and height. And we're guaranteeing this by a patented sintered wall gas flow that we introduced to the 280 machines already a few years back, and that we've actually made even better on the NXG 12600. Besides the core process, it's also quite crucial to take a good eye on powder handling. And so this is why we overall, and with every aspect of the machine, we take a very good eye on system safety and therefore operator safety. And we've been introducing the closed loop powder handling already several years back, because there's a simple saying, you do not want to see the powder and the powder does not want to see you. And so this is why we put a lot of effort in creating safe systems that are safe to use, but at the same time are still keeping capable of giving you the production environment that you need. Just really quick on the company. So as I said, we're based in Lübeck in northern Germany, right between Hamburg and the Baltic Sea. So I guess there could be worse places to work. And we've just moved into our new headquarters basically 3 years ago. We have a 24,000 square meter large headquarter where all the management is located, where all the engineering takes place, so all core functionalities are based in Lübeck. But of course, we have many other places around the world to be closer to our customers. We have some own facilities, for instance, in North America and Singapore and China. And of course, we have distribution partners all around the world, such as digiMODE. And this is really a great network of both internal partners as well as with external partners. Just to give you a quick update on the numbers. So we were the first in the industry in multi-laser machines, as I already introduced, by the dual and quad and now the 12 laser systems. It's been 16 years since the first industrial selective laser melting machine in the industrial environment. So that's already quite a long time span that we are experiencing and talking to customers and better understanding their needs. As I said, multiple patents and coming along with that, several innovations. We're focusing 100% on metal powder bed fusion. So we do not look into polymer or ceramics or anything else. It's just metal powder. We're about 450 plus global employees. Of course, the majority is based here in Lübeck, but we are starting to grow, not just in Lübeck, but all around the world. We have just about 500 machines installed the world, and if we just count all the lasers individually, we're over 1,000 installed lasers across the entire globe. And I just forgot to mention, averaging 2 lasers per machine. So there is a clear trend by our customers that is going into the multi-laser direction. And I guess the benefits are quite obvious. Of course, you cannot just focus on larger builds, but also more productive builds. And this becomes quite clear if you take a look into our product portfolio. And this is a little bit a journey through time, if you will. So basically the 125 is being the system that we've been using for the past decade. It's quite a small machine, but it's really, really versatile. It's great if you only have to manufacture small parts anyways, or if you are trying to convey a design of experiment or feasibility studies. It's super easy to clean. It's super easy to switch materials. So that's definitely a great starting product. The core of our current product portfolio is then built by SLM 280, 500, and 800. So this is our current system of machines that we're offering, ranging from mid-size to large-size machines between 2 and 4 laser configurations. And also we've been the first company that actually entered the 700 watt plus laser area. So we've been offering 700 watt laser configurations since many years, of course, boosting productivity on the one hand, but also enabling new materials such as low alloy copper alloys, for instance. And of course, our latest addition to the portfolio, the NXG 12600, built envelope 600 by 600 by 600 millimeters cubed. As I said, 12 lasers. Each of those lasers has a 1 kilowatt laser power, and we're up to 5 times faster compared to a quad laser system. And of course, we do have that larger build envelope. But today, I don't want to talk about machines, unfortunately, but rather a really cool technology, which is FreeFloat. And it's been a little while now that we've announced FreeFloat to the market. We did that through LinkedIn by our campaign, Goodbye Gravity. But actually, we want to take a few years back in time, because already in 2018, this is the first demonstrator part that we showed the world on Formnext in 2018 in Frankfurt. And back in that point of time, it wasn't really clear what we're going to do with this technology. It didn't even have a name. It pretty much came straight out of our engineering department and just happened to be on that booth. But it was definitely worth it, because many, many people approached us and wanted to see how it works, how we achieved it, if that can be put on their existing machines or existing systems, basically all of those product-related questions. But at that point in time, we weren't even there yet. But the feedback that we got from the customers was definitely that there's a need to reduce support structures, ideally already during the build. And there are a few simple reasons why you want to do that, because first of all, you're melting powder that basically does not have any larger value to it, because in the end you need to remove it, and you're basically generating waste, if you want to say it that dramatically. And of course, it's quite a manual process to remove those supports. There are a few automated processes, to be fair, but those are not really globally distributed. They're not always available, and of course they're not cheap, and there's still an additional post-processing step. And of course, I have to say that supports are there for a reason, because otherwise we would have just left them out in the beginning. So the main reasons for supports are to sort of carry out the heat and the thermal energy that we put into the powder bed out of the part, to give it or to allow it to cool down, and therefore prevent internal stresses, and also to keep the part in place. Because some materials, especially titanium alloys, they're quite prone to distortion, and those supports just keep those parts in place and prevent them from warping up. And in the worst case, they could actually do harm to a machine, because we have that recoder on top of the powder bed, and if the part sticks out and hits the recoder, then this is of course not what we want. So there are basically two reasons for supports. But with FreeFloat, we still have developed a technology that allows for a massive reduction of supports. And until that point in time, there was this 45-degree rule, basically stating whenever you have an angle that's 45-degree or lower, you would have to add supports on the bottom side of those parts. But already in 2018, we could show the world that we're able to achieve an angle of just 15 degrees without any downskin structures at all. So that's been definitely an innovation. And we also learned that it depends heavily on the geometry. Because if you take a closer look at those parts, it's a little hard to see from that angle, but here in the beginning, or here at the front, these are just flat bars. Here in the middle, these are triangular shaped with the tip facing downwards. And here at the back of the substrate plate, these are hollow cylinders like pipes. And whereas we could build those two down to an angle of 15 degrees, those pipes were a bit more difficult. So 17.5 degrees was the lowest angle that we could achieve. So already back then, we identified, okay, there's a massive influencing factor of the geometry. And this wasn't the only thing that we learned across the past few years on the way to a product. So what is FreeFloat? We've talked a lot about support structures, and of course, this is the major USP of FreeFloat, and of course, that's the overall goal. But there's a little more to FreeFloat that I just want to mention. So if you think of designing parts or part design in general, until today, you were somewhat limited in the diameter of internal cooling channels. And why? Because if you were to increase that diameter without FreeFloat, there's sometimes a natural border that you can't just build larger diameters, because then the part is just going to fail. Now, there are two ways of circumventing that. You could either adjust the shape of those internal cooling channels, that's one way, or you would have to add supports, but that's somewhat not what we want, because inside they're really hard to remove. Then you would have to use some chemical support reduction processes, and that's again not really what we want. So with FreeFloat, you can increase the diameter of internal cooling channels, but without the need of supports and without the need to adjust the shape of that internal cooling channel. Besides those two major USPs, there are also a couple of more that might not be obvious when looking at those parts, but it's specifically when we think of parts that have very thin walls or are very sharply edged, some of those fragile components. This is where FreeFloat is also benefiting. And I have a slide in just a few seconds that demonstrates that perfectly. And also some other stuff like surface finish and peel up and complex geometries. So these are just summarized all of the benefits of FreeFloat. Some more examples. So I already showed you this part here on the first slide. Now I guess it's a little better to see that we're testing 3 different geometries here. And that was, as I said, in 2018. And just a year later, in 2019, it was still a development program. but we showed the world that we now have reduced that value from 15 degrees to just 10 degrees. And by doing that, we also tested a few other things. So we took one of those demonstrator parts, so this impeller kind of thing, cut it in half, or also those those tips facing downward. And while testing more and more close to realistic parts, we also identified something else. As I said in the beginning, the geometry is an influencing factor, but of course also the length that you want to build without supports, or the span that you want to build without supports. So this is why we came up with a definition of long-range geometry and short-range geometry. And what we mean by that is basically that a short-range geometry is rather in the order of magnitude of millimeters. So basically, if you take a look at this part here, those 5 degrees were achieved here at the very top, so at the rear edge of that part, and those 10 degrees are then achieved on those flat bars, for instance. And this is rather in the order of centimeters, and short range, as I said, is rather on the order of millimeters. So there's no fixed rule that you can use. There's not just a single number that you can say FreeFloat just works until 5 degrees. You always have to take your part geometry into consideration. You always have to take the span into consideration, and there are just multiple parts that you need to consider. Also, because to be honest, nobody really builds those parts. These are just demonstrator parts, but actually something closer to this. And depending on the part, you might want to say that the actual part geometry somewhat can act as a support structure as well, because those struts here, they add support to the overall part geometry without having the need to add actual supports. This is of course good from a design perspective, but a bit difficult by just stating a single number, and therefore we had to come up with those definitions. Some more examples, because one feedback that we received from the customers when we showcased this a couple of years ago is that it needs to be a productive solution, not just because SLM Solutions has always been somewhat linked with the keyword productivity, but also if this ever is going to be used in an industrial environment, it needs to be productive. And so this is just an example that I brought here today. This part is not new by any means, so we've been showcasing this for several years now. And in this case, we built it out of Inconel 718. And this is basically the standard process that you would use without FreeFloat, and basically support every surface at an angle of 45 degrees or lower. This would then give us the support volume here, and the part builds on an SLM 280, 2 days, 14 hours, and 18 minutes to be precise. And then it takes 1.5 hours in post-processing. So we only built this part on a single platform, nothing else, just this part. And then actually took the time and took a look at the poor guy who had to do the surface finishing for this part. So this means removing all supports manually, grinding the surfaces here at the bottom to make it smooth, and this takes around 1.5 hours. Quite interesting, as I said. So this is Inconel. There are a few materials that are not really loved by the people who have to do the manual work, and Inconel is one of them. Titanium is another one. Aluminum, being a little bit a softer material, is of course easier to post-process, but still, if that's something that you can save, I think this is always good. So in the first step, we gave it a shot with FreeFloat, and in the very first iteration, we just took this 45-degree angle, divided that by 2, and came up with 27.5 degree. And already that reduction led to a reduction of support volume by 96%. So just by applying FreeFloat and by just using the angle that I know, dividing that by 2, I could almost save all support structures. The build time remained pretty much the same, so we were 2 minutes faster with FreeFloat, but quite comparable. And now what's really interesting is, of course, the time in post-processing. So post-processing for this part went down from 90 minutes to just 15 minutes. So this means either I can do 6 times as much parts in the same time as before, or I just have my one part way quicker in my hands than before. And this is quite interesting. So two major savings, of course, one is raw material. And now, of course, it depends a little bit on the scenario that you want to look at. So if it's just a small series production with maybe a few or a dozen parts, all the way to an actual series production with 500,000 or 1 million parts per year, this is basically pure money that you're saving without with FreeFloat and without supports, but also post-processing. So depending, of course, on the wages and the fee that you want to consider in your calculation, the numbers might change a little bit. But of course, if the same part is now up to 83% faster in post-production, I think the math is quite clear here. I was already very impressed by those results, but our application engineers, they said, well, we can do better than this. And so they came up with this. They wanted to do a second iteration. And this time, they really only added supports where they're absolutely needed. And so this is here at the bottom, of course, because this is where the part is linked to the substrate plate. And whenever there's really a large horizontal part, such as here at the tip or here at the top. So there are a few centimeters of horizontal parts that just needed to be supported. But in the end, we almost had no supports at all. So in the end, we almost cut out 99% of all support volumes. I couldn't include a build time. You're going to see the reason for that on the next slide. But the reason is really that we put multiple parts on a platform because this was then going to a trade show. So I don't have a fair comparison of build times, but it's going to be comparable to those figures up here. So you can imagine it's going to be around that 2-day, 14-hour, and let's say 15-minute mark. And post-processing, naturally, if you have even less supports, it just goes down to 5 minutes in this case. Let's take a look into that actual part that we built. So as I said, we built this, and now you might actually understand why it's called FreeFloat, because this part here is really free floating above the substrate plate. And just for comparison reasons, we added two conventionally supported parts right next to those parts. And this is actually my favorite picture here, because this is the downskin facing surface of exactly this part here. So basically exactly what I was supporting previously. So basically what you see here now with FreeFloat with no supports at all. And this surface has not been touched by any means. Of course, it will never look as good as a perfect upskin, or will not be shiny or anything. But for a surface that has not been supported, that is facing downwards, this is a pretty good result. And of course, since our parameters have been open and will always be open, of course, this will also give you the opportunity to further dial in on those downskin parameters to even adapt them to this specific part and make the surface even better. Depending on the actual part requirements, it depends if you would like to use this part as it is, or if it needs surface finishing anyways, because you really have high surface requirements. It's quite important that the roughness that you're seeing on one area is somewhat comparable throughout the entire area, because this then makes it easier for post-processing. And this is exactly what we achieve with this part. Let's take a look closer into the part. So basically everything that we've just seen was rather on the macroscopic scale. Now let's take a bit closer look into the microscopic scale, and I cut it some parts in half. And this is also a little bit of the history of FreeFloat and how it all started, because just a few years ago we were making trials, and this was part of a PhD study of one of my colleagues. So FreeFloat is rather a byproduct of that PhD study, but of course we're still happy that he came across that. So what we see here is a honeycomb structure. It's thin-walled. You do have some sharp edges here at the front. You do have those joints here in between. And this is basically achieved by using the standard process that we know. So it isn't bad by any means. We still get the geometry quite accurately. It looks okay. but we weren't really satisfied with it. So we really wanted it to be more perfect and just to look better. And so we experimented a little bit. And what we've seen is that we could actually achieve something that looks like this. And already by looking at that picture, I think it becomes very obvious that this looks far better than this one over here. Everything looks far more stable, far more homogenized. You can even see those individual melt tracks in here. You can, if you look close enough, you can even see the difference between the contour parameters and the hedge parameters. And this is really what we wanted. Of course, back then, this was really at the point in time where we really dig deep in our software preparation, in our preprocessors, and it was a little hidden, and we had to dial some secret knobs. So we of course knew that this can't stay the way it is, so we have to make it easier to use for our customers. But in the end, this was really the starting point for the development. And we also made several trials on surface roughness and part density. So this was basically all proving that we're on the right path with this development. I already mentioned in the beginning that there are two reasons for support structures, and one of them was actually that we want to keep the part in place, because if you add a lot of heat and thermal energy to a part, you might want to, or you might actually see a risk of distortion. And so what we did is basically we took one of those cantilevers and we built them with supports in between so that they really remain in place. And then we added the so-called profiles. And those profiles are really the learnings from, basically the learnings from the past, that we saw that by the process and how we changed the process, there are, let's say, multiple amplitudes or multiple levels of FreeFloat that I can use. So to make it visual, those effects here, they look quite dramatic, but this is rather a low impact in terms of support removal, of course, because this is then only applying a little bit more stable melt pool and a little better surface roughness and higher density, but this won't lead to support reduction in the first place. So this is what we would call a low profile, and everything that has to do with actual support reduction then goes into the medium and high profile. And basically those parts that we've built here, they've all been built with the medium profile. So the medium profile, out of our experience, works in, I would say, 90% of all cases really well. And if you have a very critical part, then we would actually recommend to use the high profile. And this was one of the learnings that we took in order to take it from an engineering standpoint, from an R&D tool, to something that actually a customer could use and make it as easy as possible. And therefore, all those nerdy details we put into those profiles, and I think those profiles are quite easy to choose from because you already know what you would like to have in the part. So we took those profiles, applied them to those cantilevers, and then after the build, we removed those support structures in here. And since this is titanium, and titanium is really, really prone to distortion, you would actually see this tip here warping upwards. So basically the part looks in the end like this. And then we had 6 measuring points, and then basically just measured the delta compared to the state that it was before removing those support structures. If we don't use any profile at all, so really just the standard titanium parameter that we already know, we would end up with, well, of course, quite a high distortion. We didn't do any stress relief or anything, so this is as built. And then you can see that those profiles, low, medium, and high, low does not have a significant impact. It improves a little bit, but really the large impact is then on the medium and the high profile. We also added a global profile. This is meant to be used if you would like. You can turn the global profile on as a fallback solution. So basically, in case you might have forgotten to apply a certain profile for a certain region of a part, this global profile then comes in and sort of adds a little bit of free flow to the overall part to just prevent it from really warping up, but it doesn't do the same as a medium or a high profile. So let's take a quick look into the FreeFloat workflow, and then I would love to give you a very, very quick demonstration, because the workflow inside the software is really simple, and I think it's just better to take a demo and walk you through the individual steps rather than just showing it to you theoretically. So today the process looks like the following. So we start with an SLM file, and this SLM file comes, of course, by our data preparation, so the part geometry, and then you can use Magics, for instance, for that. You add the support structures. You then go into the metal build processor, you slice it, you add the parameters to the geometry, and this gives you in the end the SLM file. And this SLM file is then transferred to the machine, loaded into MCS, and then basically the part is built. So very simplified, but it pretty much pictures really well how the process today looks like. With FreeFloat, the process still looks very much the same, except for two changes. So we still start with an SLM file, but with reduced support. So already when you start creating a new build file in Magics, you need to consider that you're using FreeFloat afterwards, so that you can already start reducing support structures as we did it here on this slide. So starting with this and then coming up to the end where the part is basically using as little supports as possible. So you, of course, you do that in Magics, and we're also working on a technology that does that automatically, but this will take a little longer. So in the first step, we'll start with this, and then there's a second step in here. So that's the FreeFloat desktop software, and the actual goal of that software is really to assign those profiles to the parts where they're actually needed. And then in the end, this creates another SLM file. This goes onto the machine, and then in the end, you have the part at your hand. All right, I think I'm still quite okay in time, so this allows me to just show you the software, how it looks like, and you should be able to see a desktop software. This is in a beta state. We're about to release it in just a few weeks, but this is basically the beta phase. It has the same functionality. It looks pretty much accurate to the final product. It just is not the final product. So how does it look like? So I do have several tabs here on the left-hand side. I have a large screen here in the middle, which is basically the area in which I can have a look at my part and basically, well, you're going to see it in just a second anyways. And then on the right-hand side, this is the so-called advanced edit area. And this is then the place where you would add profiles to your parts, where you can select parts, where you can select application ranges, and that's really it. So in the beginning, you need two data files to start with. One is the so-called SV data file. So this is going to be the FreeFloat data file as soon as we release it. And this software file, or this data file, basically contains the profile information. So we've talked about low, medium, and high, and the information is then stored in those in this SV data file. And I need, of course, an SLM file already hatched and sliced and added with a parameter. So I'm just going to load this in. This is a demonstrator part that's, but basically this applies for everything. So now you have a visualizer here. So to some of you, this might already look familiar. If I use the horizontal bar here, I can see how the part is being scanned on the machine. And by using the vertical slider here, I can see how the part then progresses over the build height. I can also select multiple machine configurations. So right now that's for the SLM 500. You could also apply that for the SLM 500. Or if you are having a larger system, hopefully very soon, this is then also being considered in this software right now. All right, as a default setting, we decided, and just based on the experience, that the medium profile really works best in, I would say, 90% of all parts. We decided to apply the medium profile to all parts as a default setting. So what does that mean? If I take a look here into my part list, you might want to use a little better part names than I did here. But basically what you can see here, that's a part name. It shows me that the medium profile is assigned to this part throughout layer 1 through layer 400. And in this case, that's the total part height. If that's okay for me, and I would really recommend in the first stage that this is basically the first trial to continue. I can already hit export, and then I would get a new SLM file that adds those profile information to the existing SLM file, and then can be loaded into the machine. So it's that simple. I didn't even do anything here, so it just applied that profile right away, and I would be good to go. But just in order to show you how easy it is to manipulate those profiles, I'm just going to show it to you. I can select multiple parts if I want, so I can make those changes to multiple parts at once, or I can do that part by part as I like. Let's just go with this part here. Here's my profile selection. We already talked about low, medium, and high. If I want to use the high profile, I can click high, click apply profile, and now the profile has changed. Same, of course, goes for low, and that's already it. The reason why we're added those application ranges is really that the part does not always require applying those FreeFloat profiles throughout the entire height. So let's take a look into this part here again. Basically, where we are really saving a lot of support is here in the bottom half, and then here at the top. So this is, in this case, where I would only add those profiles. And I can do that if I want. So let's just pretend this part that I'm working on is that huge light hinge part. I'm going to use my medium profile here again. And now I'm going to select the application ranges. So starting from layer 1 to layer 200, and I can hit apply. It changes here above. And since I just need to add this for the top section as well, I can add, let's say, just for the last 50 layers, I can add that as well. And this is how I can select those application ranges for each part. Also, if there's a part that does not require FreeFloat, maybe just because it's something that you want to use to mark your platform, or it's a density cube, and for whatever reason, you can also select none and click apply. And this is then basically taking any profile information out of this part. Now there's a little warning sign. If I head over to the messages tab, it just says no FreeFloat profile assigned. I can still export, but since the overall purpose of that software is to add profiles, it just gives you a little warning that you might want to take a closer look at that. And that's it. So it's as easy as that. I can now click export. I can type a new name in here and press enter. I now see that progress bar here at the top. And as soon as that's at the far right, and as soon as the export button is working again, this is it. So it now just created a new SLM file, including that information. The part file, and I'm done already. So the part size is about 70 megabyte. Of course, it depends a little bit on the part file size. Might take a little longer for higher builds, but it's quite quick in processing. And of course, this was crucial for us. And now I would just use this SLM file and load that into the MCS, and I'm good to go. All right, before we jump into questions, I just want to briefly talk about product availability and requirements. So we've validated FreeFloat with 3 of our product lines, so the SLM 280, 500, and 800. Don't worry, we're working on FreeFloat on the NXG as well, but since the NXG will be available next year, we still have a little bit of time, so we'll also consider FreeFloat for NXG, of course. But for now, we'll focus on 280, 500, and 800. The good news is FreeFloat is retrofittable. So if you already have one of our machines in place that matches this requirements, we can sort of adapt to bring the machine up to the latest level, and then it's ready to run FreeFloat. What does it need? So we say that it needs the latest CE2 gas flow configuration. So that's the gas flow configuration with the sintered wall on the right-hand side. And it's important that this needs to be there from the beginning. So no gas flow upgrades, but really true CE2 configurations. So for the 280, this is true for 280 2.0 and newer, SLM 500 1.1 and newer, and SLM 800 always had this gas flow configuration. The machine needs also to run on MCS 2.6. This is required because we're adding information to the SLM file, and the MCS needs to interpret those information. And so this is basically just the reason why we need to add a new MCS. And from a hardware perspective on the machine, we recommend to use a recoder brush. It's not mandatory, so the software FreeFloat still works with the recoder lib anyways. But if you are new to the technology, or if you're making trials in the beginning, we just recommend to use it because it gives you a little bit more flexibility. Because if you might go too crazy and reduce just all supports for a part that actually needed at least a few supports to keep it in place, and if it then pops up, the recoder brush just adds you a little bit more process stability, just by the fact that there are a few bristles before hitting the actual recoder. And of course, the new desktop software, that's basically the software that I just showed you. And we're going to start with two materials first. So Inconel 718 and Titanium 6.4 are going to be the first two officially released materials. We're going to add more materials, of course, over time, but we decided to focus on these two for the start. So we officially announced FreeFloat in June of this year. We're going to release it in the 4th quarter of this year. But to be a bit more precise, this is going to take place in the following week. So we're very close before product release. All right, with that, I would be done with my presentation. I would like to thank you already for your kind patience and attention. And I would say we go now into the questions.
Okay, thank you very much, Benjamin, for your presentation. Actually, we had the question, but at the same time you answered it. I mean, Mr. Burch asked that, is there any material restriction about FreeFloat? And you said that in your presentation, titanium and Inconel are available now, but I mean, for the next period, you are planning to add new materials like aluminum, like other materials which can be used at SLM systems. Actually, I want to ask a question. Why? Are you developing some parameters for to be able to use FreeFloat specification for these materials? I mean, why it takes time?
Mm-hmm. That's a good question. So in general, and maybe let's take a look into this process overview here again. So there are basically two relevant things that you need. So first of all, in order to create that SLM file, of course, you need material parameters. And then within FreeFloat, you need those profiles that we've just seen. And in order to create this SLM file here, we are developing parameters that work specifically for FreeFloat. So of course, we've seen those profiles already do quite a lot of improvement for the part. But in order to really get the maximum out of it, we adapted the parameters just to make them really fit very well with those profiles. This is of course why it takes a little time. We're also taking multiple part geometries for validation into consideration. And you might have already seen those impellers and turbocharger housings, so multiple parts. And out of this experience, we're developing one set of parameters that we think works best with FreeFloat. But as I said, it's not mandatory. So the customer already has his or her validated material parameters. Of course, there's no restriction in using those. So this would work as well. And maybe just one final comment on the material selection. So you're absolutely right. We're going to add more materials to it. Currently, I'm planning with at least 2 more new materials per year. And also, as we start developing more materials, this is going to be a default for new materials that we add to our portfolio, that we already ship and develop FreeFloat parameters with new materials as well.
Okay, perfect. Thank you. Actually, Mr. Çağrı has a question. He said that, do we need post-process for downskin parts? What would be the rawness?
Yeah, it always, I guess this is the the most given answer in an additive. It always depends on the part. And of course, it always depends on the exact requirements. So if we take a look into, excuse me, when we take a look into those parts here again, so in this case, we really were fine with the surface roughness that we achieved in this part. I would have to look up the exact area value, but I can definitely provide that, because we wanted to show it in the as-built condition, and even though if it was a part for a trade show, we didn't want to make it look, you know, super shiny, so we just wanted to leave it as it is. In this case, it was okay. We also have customers that just based on a business case calculation, and of course based on part requirements, they are okay with the as-built surface roughness, just because they say it might not be a part that's dynamically loaded, it's rather a static part, or I can live with a certain surface roughness. It always just depends on those requirements. Of course, we also have customers that really want to have a perfect surface roughness, and then of course we cannot achieve that with a process that involves metal powder particles, because there's just, you know, a physical limitation in reaching a certain surface roughness. So there is definitely a surface roughness, a post-processing step mandatory. The good news though is that if you want to use surface roughness, because the overall surface roughness is sometimes rougher than you need it to be, you can take the part off the platform from FreeFloat, and then basically go directly into post-processing without having to remove those supports beforehand.
Okay. Okay, thank you. Actually, I couldn't see more question in my screen. So if you have any question, please type it, because we have still 10 minutes to close the session. So we can answer. Benjamin can answer. So, okay. Benjamin, I want to ask you again a question. Do you think that we can, for the, next, 2 years, 3 years, 5 years, whenever it will be happen, I don't know, but do you think that we can get rid of all the support structures in the future?
I hope so.
Okay.
I really do. The question is if, well, of course, if we're going to achieve it, but taking all the, let's say, the material science and physics into consideration, I think supports will remain, and as I said, they do have a right to exist in some cases. And the overall goal with FreeFloat is, of course, just to reduce them where they're not absolutely necessary, because in the end, they're giving us a hard time in post-processing. They're causing manual labor, causing time and effort, and basically, as I said, we're generating waste with that. So if there's a way to reduce them as much as possible, this is exactly our core goal. If at one point we're going to completely live without supports, let's see what the future is going to bring us.
Okay. Okay. Actually, I don't see any more questions, so I can, thanks to you, I saw one. Okay, Mr. Hüsnü asked a question. Whitney, can you say absurd density percentage? Actually, I think there's a typing problem. Okay, I will look at your question again, Mr. Hüsnü. Mr. Cemil has a question. He said that he couldn't catch the beginning of the webinar, so is there any possibility that you can explain what does FreeFloat make for zero support on any part?
So what FreeFloat is, or what was the question again?
Actually, what does FreeFloat make for zero support on any part? What does FreeFloat do on the part to have a zero support on it, on
Okay,
it.
sure. All right. So yeah, first of all, although we use the word support free and try to reduce supports as much as possible. As of today, there's always a limited need for supports, and FreeFloat's goal is really to go with as less supports as possible. But yeah, we just had the discussion if there's going to be 0 supports in one point, but not at this point in time. But we're definitely focusing on that. Just to give you a quick update on what we do from a technology perspective in order to allow this. And I think this slide here summarizes it quite well, especially here on those 2 examples here in the beginning. So as I said, this was the first trial that we built with let's say the conventional supporting that we would do. So using supports up to 45 degrees. And then in the next step, we used the same part, but just cut the angle that we used to identify those supports, cut that in half, and basically led to that support reduction by 96% and post-processing of 83%. And I also mentioned that the build time is somewhat comparable. Well, in fact, FreeFloat is a little faster here, so it's 2 minutes faster. But let's say it's somewhat identical, and I think this is already part of the answer that I would want to give you. That while we're bringing a lot of thermal energy to the process, supports in one point were needed to get the heat out of the part and allow the part to cool down. But there are, of course, multiple ways to achieve that goal. You could do that either via a solid support, or as you can see here on this slide, since we're having a comparable build time but way less support, we noticed that we can just use the overall process time way smarter, and not use the time to just use to scan supports and therefore melt powder that we would have to remove in the end. But therefore just still use the time a little bit wiser and just allow the process by itself to cool down a little bit, therefore decrease the temperature of the part before we then scan the next layer. And so this is of course one of the learnings. There are a few more that we have identified over the past weeks and months. Well, actually not weeks, but really months and years rather. And also that as I guess it's quite obvious that we're just focusing on the downscan areas because this is then the connection to the supports. So the parameters that we're adapting are, of course, focusing on those downscan regions very much. And one crucial step is also that we took a look into those downscan regions, and we've come up with basically a handful of solutions that just increase the efficiency of assigning FreeFloat to those downscan areas. And so I would say it's a combination of those two that allow to reduce supports, not to 0, but at least to a minimum.
Okay, thank you. Actually, there is also one question. Do the beam diameter and ambient temperature change during the application?
If the beam diameter changes during?
Yes, during the process.
No,
or
not,
ambient temperature change?
No, not really. No, I think this is well, the beam diameter does not change. We on the, let's say, 280, 500, 800 systems, we're using a fixed diameter. We can work a little bit with setting a defocus, but this is not something that we use for FreeFloat. On the NXG12600, indeed, there is a function that's called the zoom function. And then this is really a mechanical or optomechanical process that allows for changing the beam diameter from very tiny to rather large. And this is something that we could use for FreeFloat, but on those 280, 500, 800 systems, this is not something that we use for FreeFloat.
Okay, Mr. Husni asked his question. What about density improvements after FreeFloat and also strength improvements? He asked.
Yeah, so this is also, of course, quite crucial. And also, when I said that we're releasing 2 materials, this also means that we're adding a lot of the data that we're generating from mechanical testing, from density testing, with that. So of course, we'll have that already for the product release, but what I can already say is, for instance, regarding density, we've built several parts that had a very comparable relative density than a conventional process. So we're targeting always to be above 99.9% relative density, and this is also what we're achieving with FreeFloat. And also, just to give you one other example where we successfully used FreeFloat, was during was for a customer part. I cannot give any more details on who it was and what kind of part it is, but so the requirements were really strict. And in the end, we had to CT scan the entire part, so they wouldn't just have a section of the part and then just grind and polish it, but they really wanted to have a CT scan for the overall part to identify pores. We built this part without any supports with FreeFloat. So overall, the whole part still achieved a 99.99% density, so we didn't see any larger pores or porosity. So we were lucky because we were achieving, of course, the customer requirements in this case, but it also just was another proof for FreeFloat that it works also on, let's say, critical components with high requirements on density.
Okay, thank you. There's also one question from Mr. Cenk. Would you please explain the algorithm logic of the software in more detail on support generation? How does the software decide proper support types and areas? Is it coupled with any physically simulated data?
Yeah, so as of today, let's take a look into the workflow again. So as of today, we're still starting with the SLM file, but in this case, in order to create this SLM file in, let's say, Magix, this is right now something that you would have to consider during creating that part or in preparing that part. So already when you have this part here and you're preparing the build in Magix, let's say, you would already have to assume that you're going to use FreeFloat in the end. So there you're not using the, let's say, the auto support function with 45°, but either use another angle or just use supports and add them manually during the process. As I said, this is the first version of FreeFloat where this sort of manual consideration of supports is necessary, but we're already working on a solution which uses, well, two approaches in the end, but basically we're considering simulation on the one hand, and on the other hand, we're also using the part information that the part already has and use that in order to add supports only where they're needed. But since we had to really finalize the product development for the version 1, we had to put that into version 2. But we have multiple ideas of how to realize that, and I basically can't wait to have this feature available. And so this is why in the first step we're relying on that manual process, let's say, with support settings.
Okay, thank you. I hope it will be enough for Mr. Cenk. Okay, I don't see more questions in my screen. So, Benjamin, thank you very much for your presentation. And I will turn in Turkish, and I will thanks to all the attendees. So I just want to thank you.
Thank you very much. Thank you for having me. These are just my contact details. So if there are more questions on FreeFloat, feel free to reach out to me. Thank you for your attention. I can't say that in Turkish, unfortunately, but thank you and enjoy your day.
Okay, thank you. Herkese çok teşekkür ederiz katılımınız için, sorularınızla katkılarınız için. Herhangi bir sorunuz olursa Benjamin'e, bana her zaman ulaşabilirsiniz. Yanıtlamaktan mutluluk duyarız. Bu arada bu tarz etkinliklerimiz devam edecek. LinkedIn hesabımızdan digiMODE'u takip ederseniz orada bu duyuruları çok en azından kaçırmadan bilgi sahibi olma şansınız olur. Tekrar teşekkür ediyorum vaktiniz için. Bir sonraki etkinlikte görüşmek üzere. Hoşça kalın.